Okay, good morning everyone. So last week we have already discussed related to the issues of the interface charge, and then we will see some influence coming from the interface charge, especially related to the CV curve. We see some stretch out, and for today we will start to describe some of the most common way to evaluate the interface state density, and one of the popular estimation method for this DIT interface is what we call the low frequency, or we just consider as a quasi-static. The low frequency method, or we just call as a quasi-static method. So the basic theory of this quasi-static method was developed by this researcher. If you are interested in the how this method is coming from, you can refer to the reference in this textbook, which is a very nice textbook that very detailed to include all kinds of different characterization methods, including from the materials and also for the electrical results. So that's a very nice the toolbox that we will use very often. So anyhow, the low frequency capacitance can be derived from this equation, and therefore once we consider the influence coming from the interface state density, and in the end we can have the DIT can be calculated as a CIT over Q squared, and therefore we can have this interface state density estimation coming from this equation. So the lower limit of a DIT that coming from this method can be determined with quasi-static techniques around like 10 to 10. So that's a resolution of the interface state density coming from this method. That will be around 10 to 10. However, as the oxide thickness decrease, if the curve contains a certain oxide leakage current component, then therefore if we continue still use a quasi-static method, that could pose some question if we are trying to measure the DIT in the leaky dielectric. So that's one of the issues for this quasi-static method. So this is how we already shown in the last time. This is also the another description here with comparison of with DIT. This is an ideal case that we don't have the interface state density, but if once we have the interface state density, we will see the difference in the CV curve. That's also the one of the very obvious evidence that how this interface state density can influence our CV characteristic. And for sure that we will not only have one method. To be honest, we have many methods that allow us to characterize the interface state density. And the next one is a very popular one that we call as a conductance method. So the conductance method was proposed in the early time from the 1967 so far, but still considered as one of the most sensitive method to determine the DIT. Is also the one of the popular method to determine the DIT. And then also the interface trap can be detect as a lower as a 10 to 9. With this kind of order, that still can possibly to be detected from the conductance methods here. And with this conductance method, that there's several assumption and consideration if we try to consider the conductance method. So if we consider as a MOS capacitance with this equilibrium RC network, so this is a contribution coming from the oxide capacitance. This is contribution coming from the substrate capacitance. But now we also have to take into account the contribution coming from the interface state density, which first of all we can consider as a resistance coming from interface state density, and also the capacitance coming from interface state density. So in the beginning, we consider this as using the RC component to try to describe the characteristic of the interface state. And then furthermore, we can try to reconsider this network as a parallel capacitance versus the parallel. This is a parallel capacitance versus a parallel conductance here. So the GP here is what we call as a parallel conductance. It's what we call the parallel conductance here. And then with this equilibrium consideration that we use parallel capacitance in parallel with parallel conductance. But however, in reality, when we try to do the measurement, we can only get the result of the measured capacitance and measured conductance. So this is a real measured results. So that's actually the real measurement results. So therefore, what we have to do is try to compare this measurement result where we have the measurement conductance here to equal to the case with this the parallel capacitance and then the parallel conductance, and therefore with equal of this one is and this one, then we can simply to calculate the correlations between the GP, that's our parallel conductance, versus our measured conductance and measured capacitance. So again, we try to use parallel conductance to model the influence of this resistance and capacitance coming from interface state density. But in reality, we can only measure this part. So therefore, we try to put this one, which will be equal to this one, and therefore we can get the result of the parallel conductance versus the parallel, the measured conductance, and then the measured capacitance here. And also in here, the omega here is equal to the 2 pi f. And with further calculation coming from this equation, then we can get the result. This is a very simplified conclusion where, since we have the GP here, so we can put the GP in here. Then we can start to estimate our interface state density, where will be roughly equal to 2.5 over Q times this GP omega at the maximum value. So that's a very easy one to estimate interface state density. But for sure, if you are interested in how to derive this equation, you are welcome to look at this textbook. As I say, this has been developed from 1967. I believe you can find many literature, basic material to talk about how to derive these equations. Then we will start to illustrate how we actually state by state to calculate by using the conductance method to convert to the interface state density. Because of you can see now the DIT here is related to the parallel conductance, but also related to the omega, which is proportional to the frequency. So therefore, the DIT here must be the certain frequency dependency. So if you have a different frequency, you might see the different transconductance and different peak. So let's use one example to illustrate that how we can, from the conductance versus a frequency plot, in the end to convert to the DIT versus energy level. So when we talk about the interface state density, in the end, if you try to look at the literature or published result, everyone will prefer to plot in the end as the interface state density versus the certain energy level, where the energy level can be referred to the conduction band or referred to the valence band. In this case, which is a trap energy level, referred to the conduction band here. So this is EC here. But how do we get this plot? So let's do the one by one. So first of all, from the previous equation, we have already know that we have the GP here, we have a frequency here. So basically, with a different bias, we can start to make the graph like in this way, where we have the conductance versus the frequency. And in the case with the conductance versus a frequency here, then we can start to have this graph where this is one conductance versus frequency, another conductance versus frequency, then third conductance versus frequency here. And as we already mentioned, what we are interested in is a maximum value here. So therefore, we have to identify this peak here. So the peak here, where is this one? If we look at the peak here, then we can identify the peak of this part. This is a GP omega at the maxima. So that's a maxima here. And this is also another maxima, another maxima, another maxima here. But you might wondering that how this graph is original from. Actually, this graph is original from the very simple measurement result, where we use the starting point is always coming from the CV curve, capacitance versus voltage here. So we will have one CV curve, and the typical CV result might be look like in this way. In here, probably it's better to consider as just a moment. So typical CV might be look like here. That's a full CV curve from the accumulation to the inversion here. But once we have start to sweeping the CV with a frequency, for example, from the 1K Hertz to 1 megahertz, and once we take into account the impact coming from the interface state density, then you will start to see your CV curve will have this kind of distortions. Something like this one. So that's one of the typical case, not the universal case, but one of the possibilities. That's once we go to higher frequency, then you will see there's a distortion. But here we call the frequency dispersion, or call the CV dispersion. So this kind of the dispersion that proves that we have a huge impact coming from the interface state density. That's why, because you see the previous slide also mentioned in here, we have see once we have this DIT increase, then you will see there's inconsistency here, and there's a shift, and that's an indication of the impact coming from the DIT. So therefore, if we try to measure this in the multi-frequency, we will also expect to see this kind of result. But in here, we are not only measure the CV, but you can see, because from the conductance method, what we are actually measure here is Cn versus Gn here. So that means in the characterization machine, no matter in the Keysight or Keithley, whatever the characterization machine, we can generally select the module inside, and then we can select the module where we can measure the Cn and Gn. So therefore, we are not only have this CV, actually this should be the CMV, because that's a real measure capacitance. That's including all of the ideal and non-ideal effect, where ideal means the outside capacitance, non-ideal means that we have the influence come from interface state density. But at the meantime, we can also have the curve which has a parallel conductance, which is a Gm here, and versus the voltage here. So this is something that we are really interested in. And then the typical case of the typical result for this Gm is normally we will see the Gm has a large, at the low frequency, usually has a very, very flat. But at the moment where we see this dispersion will be the moment we start to see the small peak of this conductance, because that's a reflection as a interface state density. And then once we go to high frequency, then you will see this peak will get more and more pronounced, and the peak is going to very high as we increase the frequency. So that's a frequency increase. So that means that at a higher frequency, we see the higher conductance. And then if you look at this formula, the higher conductance, that means the higher interface state density. But next one is how do we convert this one to this one? But now you have to understand that this is a Gm versus a V at the consideration of a frequency. So therefore, now we can convert the one fixed voltage, for example, here. This is a 1. For example, this could be the one at this voltage. Like for example, probably like 1 volt. This is a VG 1.5 volt. This is a VG 2 volt. This is a VG 2.5 volt. So once you can try to consider the different voltage here, and then each voltage, because each voltage you have the multi-frequency, so then you can convert the frequency into the x-axis here. So we can try to have the voltage from the 2 volt, 2.5, oh sorry, 1 volt. 1 volt, 1.5, 2, 2.5 volt here. Because now for the 1 voltage here, you have this frequency this frequency, this frequency, this frequency. So you have at the one particular voltage, you have the multi-frequency from the 1 kHz to the 1 megahertz. So you can convert the data set back to here, and you will see this kind of a graph here. And then once we are able to build up this graph, and then the next stage is that we can start to convert the DIT. So DIT will be directly calculated from this one. This is a 2.5 times this value, right? From this equation, we can know that this value times 2.5, that will be equal to the maximum, the interface density at this frequency. But how do we convert the frequency to the energy level? Then we need to use the equation in the right hand side, which is by considering the emission time constant here. So now, because this one is a frequency, so actually we can convert the frequency to the tau, right? Because of 1/f is equal to the time here. So then we can convert the frequency as a tau, which is here. So therefore, this y-axis, no, sorry, this x-axis can be able to convert to the tau, which is a time constant here. And now, because we have this 10 to 4 frequency, so that will be roughly equal to 1e minus 4 seconds, which is here. So therefore, we can use this one to be able to convert to the energy level. The energy level shown me here, which will be roughly equal to 0.43 electron volt, and which will be this here. So state by state, we have this low frequency equal to 0.43 electron volt. We have a little bit high frequency, this will be go to the 0.4, and the highest one, which will be go to the 0.32 electron volt. So now you can see that the higher frequency here is able to characterize with a shallow energy, shallow trap, which is pretty makes sense because of the high frequency. We are trying to characterize the time constant with a very small time constant, and the small time constant means that this defect or trapping event must be in the very shallow region. So therefore, we are able to characterize the shallow defects here, or shallow interface state here. So this is a typical procedures. So by using this emission time constant versus EC minus ET, we are able to build up this plot. And this plot is very sensitive for the different material. If you are using the one material, you have to build up this graph again. If you have a different material, you have to build up this material again. And in the homework, we have one homework 3 will ask everyone to try to calculate the DIT by using this conductance method. Because although if you are first time to listen the way how to do the conductance for DIT, it might be a little bit not straightforward in the beginning, but with the time pass by, you will realize that this is a pretty common method. So, but in anyhow, still have to try to understand or go through once and how this can be able to calculate for the interface state density. Okay, so another very popular one methodology here. Another very popular one methodology here is what we call the charge pumping here. These all methods, what we are introduced in this class are very classical, and then it has been developed for more than 30 years, but nowadays still very popular to characterize this advanced semiconductor. And the one, another very old one, but also still very popular, is called the charge pumping. And you can see the first paper who talk about charge pumping, which is coming from the literature in the 1969. So that's the first paper to discover the effect of the charge pumping in the MOS device. And later in the 1984, the first author, which is the previous professor in the K. Leuven, the professor Hosanaken, who actually start to find a way as a very reliable approach for the charge pumping measurements in the MOS transistor. And actually that's his PhD work, that when he was still a student, he started working on this charge pumping. So you can see that this is very old, and then but it's a very classical, and then with the time passed by, the people start to feel like the charge pumping is one of the most effective way to detect for the interface state density. So what is a charge pumping? This actually combines two steps here. First, we need to have the electrons are captured on the traps here. And then the second one is we try to pump the holes. So if we try to pump the holes, then the holes can be recombined with trapping electron. And therefore, we start to have this charge pumping current. The current is mainly due to the hole recombine as an electron. And this will cause the current. And this current is proportional to the density of the trap. So the idea behind is very simple. First of all, we try to have the induce a huge amount of electrons, and we try to make sure that electrons are being captured by the traps. And later we start to pump the holes, and we try to make sure the holes will be recombined as this captured electron, and then become as a recombination current. And for sure, this current is proportional to the density of the traps here. So here is a typical measurement setup here. So we apply the gate bias here, and we try to measure the substrate current. How do we measure substrate current? We just try to have the current trace current meter from a substrate. So once we have this the whole current recombine with the electron induced current, then we measure this current. So here is a typical the bias operation condition that we try to sweep in our MOS device between the accumulation to the inversion. So in the beginning, we will bias at the VG minus VG here. So as you know, when we bias a minus VG, that should means that we try to operate this transistor in the accumulation mode. And then the second stage is that we try to give the positive bias, VG larger than VTH, which will bias this transistor in the inversion. So first of all, we have to identify the flat band voltage and threshold voltage for our MOS capacitor and MOS transistor, which is not that difficult. So first of all, we try to bias the accumulation, and once we bias accumulation as shown in the here, that means that right now all of these defect interface trap are above our EF, above our Fermi energy here. So once the defect above our Fermi energy, what does that mean? It means that right now this interface state these defects in the interface are empty because right now they have no chance to access the electron because electron is always below the Fermi energy, right? So right now this is empty state. So that's the first state is we just want to make sure that our defect state are empty, there's no capture electron. And second, we bias in the inversion, which is give the positive bias here. But now these all defects are start to below our Fermi energy. So once this defect below our Fermi energy suggests that now we try to make sure that this defect state starting to capture the electron. So we have a lot of the electrons capture in this interface state. So that's why we bias in the second region as a B here. So the whole procedure is shown me here. The first one, as I said, the accumulation, the purpose for accumulation is just we want to empty the state. We want to make sure that there's no any trapping in the accumulation, and we start to bias in the strong start to bias in the inversion. In the second one, that would be, this is a case where VG start to approach to the VTH. So right now, we will start to foresee you will have some electrons starting getting captured by this interface state or defect state. And then the third step is we want to make sure our VG is larger than VTH. So therefore, at this moment, all the states are filled with our electrons. So we have a many capture electron here. And finally, we will come back to, again, for the accumulation, assuming here. But now, we start to have the holes created in this interface. And because we have a holes, so the captured electron are able to recombine with these holes. So this hole will recombine the electron, the trapping electron. So right now we start to see the amount of the current can be sensed, especially from the substrate, because now the hole is recombined with electron, the trapping electron. And therefore, the current where you measure from the substrate can be characterized from this equation. And then we can see from this equation, we have the NIT here, where is the interface trap density. And also, this is highly related to our frequency here. This kind of a frequency dependency is the same like the one we see the previous conductance method, that our interface density is always related to our frequency. So by sense the substrate current here, we are able to start to estimate the interface trap density. So let's look at some of the real degradation results. So this is the experiment conducted that after the CCS, which is constant current stress. So in the case with the CCS or CVS testing, we can see there's a certain increase of our interface trap. So in the left-hand side, we can see that with the no stress, which our CV curve look like in this way. So that's fresh. But after the certain of the time being stressed here, then we can see there's a certain distortion, there's a certain shift, there's a certain dispersion in our CV, which is this one. So that's as evidence that we start see the interface state density increase after this stress. So this was done on the capacitance here. But one of the great advantage by using the charge pumping is that we are able to measure on the transistor. So we don't have to use a capacitor, we can use the transistor here. And then if we look at the transistor for the charge pumping measurement, what we are interested in is the charge pumping current. And then we can see this is in the beginning, this is a fresh pre-stress as shown here. But after 100 second stress, so we can see the charge pumping current is increased, which as long as the charge pumping current increase always suggests the proportional of the interface state trapping density is increased. So therefore we can use this way to characterize our interface defect. So here's some more detail that what can be the influence on the MOS performance, especially in the case when we talk about the interface state density. For sure that we are able to see the influence on the threshold voltage, and also once we have a huge amount of the DIT, then we are very often to see the mobility degradation. And then the mobility degradation is mainly due to this Coulombic scattering, where we have a loss of scattering, and loss of scattering will cause degradation of the transconductance, and then cause the drain current degradation. And for sure that we are very often to see the DIT will also influence our subthreshold slope and also increase in noise here. Okay, so that is a part related to the interface charge, interface state density. But now we will move to the further issue is more generalized, that try to evaluate the overall influence coming from the interface charge, or even the different trapping in the dielectric. And in here we would like to introduce these kind of issues. For previous slide, we know that DIT will influence the threshold voltage. So the threshold voltage can be the certain important characteristic when we talk about reliability. So this is a typical case for the CMOS inverter here. So CMOS inverter combined with NMOS in the bottom and PMOS in the top region. So in the case with the NMOS in the bottom, the device will mainly operate, once the device turns on, is operate as a VG is larger than 0 volt. But if we try to bias the VG larger than 0 volt with a certain timing here, then you will very often to see the threshold voltage shift with respect to the time, as shown here. This is threshold voltage start to shifting, getting more and more shift as a time increase here. And also this increase is related to the gate bias. As long as our gate bias larger, the threshold voltage shift is increased. And because of this delta VTH is generally related with our bias, our temperature. So that's why we call as a name as a bias temperature instability. And in this case, this is under the case with a positive bias. So that's why we call this as a PBTI. And similarly, in the case with the PMOS, the device is biased with a negative gate bias, and we still see the obvious, the threshold voltage shift, even at the case with a negative bias. So that's why we call this as a negative bias temperature instability, NBTI. So let's look at some of the historical data related to BTI. So you can see that the BTI already has been as one of the key reliability issue from early time, but it's getting more and more papers in the last 5 and 10 years to focus on the understanding and then try to characterize and try to solve the BTI issue. And for sure that there's another several very important issue like the hard carrier injection, where we have just previously briefly mentioned, and also in the next chapter we will talk about the TDDB. So in general, the bias temperature instability BTI can be considered as two cases. One is NBTI, another one is PBTI. And normally what we observe here is a threshold voltage or flatband voltage shift, and that can be due to the creation of interface state. If we try to use a charge pumping CV, DC, IV, then we will see the influence coming from this BTI effect, and then this also will be able to recovery with the time. And when we talk about recovery, sometimes it's mainly due to the detrapping, but not all of them is due to the detrapping. Sometimes we have some additional issues here. So this can be ascribed to the several possible reasons. For example, the positive oxide charge, the negative oxide charge, that depends on what kind of dielectric you use. That's also related to creation of the interface state here. So this is become very important when we have this silicon oxide nitride, which is used as an NBTI in the PMOS, and then in the early time of a hafnium oxide, also suffering the huge PBTI effect. So this is a BTI data. This is a real measurement data that are published in the literature here. So the BTI can cause, as I said previously, there are many causes of degradation of the threshold voltage. So you can see the first graph, which is the threshold voltage versus the time here. So if you try to plot the threshold voltage versus the time, and then if you set the criteria that your customer can allow, that you can allow is a maxima for 30 millivolt, and then you will see if this is a case of the 30 millivolt, in the end, the overall lifetime for this semiconductor, for this device, is only 10 to 4 seconds. So now you can see that if our device suffering the huge BTI effect, in the end, the lifetime can become very short, very small. the 30 millivolt of threshold voltage, which is a very, very small value, but actually that's like industry, they hope in the end to achieve this kind of a small threshold voltage shift. And also in the middle graph is another example that when we do the positive stress for the 10,000 seconds, so then we will see the drain current degradation, and also after stress we see the gate current increase here. So let's look at some of the papers. So the first identification of NBTI, that's already coming from the 1966. From 1966, so now you can see that actually all the reliability issue has been discovered since the beginning of the semiconductor, but since many times it has been more than 60 years for the semiconductor. We're still suffering this issue. The reason we're suffering this issue is because of our technology is being involved. We have a new semiconductor technology, we have a new substrate, we have new material, and also our bias condition is getting more and more aggressive. And then we have also have more and more aggressive system performance. So that's always push the reliability issue is always coming again. But the good thing is that once we understand reliability I believe for your whole lifetime, that will be all useful for your whole lifetime, because you will meet this issue again. So that's from 1966. That's already have the literature talk about the surface charge density, which is very sensitive to the NBT. What's NBT? That's a negative bias temperature. Treatment. So this is a measurement of the flat band voltage versus applied voltage. So now we can see the flat band voltage is a certain shift. This is a measurement of flat band voltage after 300 Celsius degree treatment. But at the moment, there's no study on the time dependency. So only for this literature, only reported as a bias dependency. So there's no time dependency here. And later, 1 year later, we try to discover more and more about these issues. So this is the first comprehensive study of the NBTI and PBTI that's coming from 1967. So this is discussed of the sensitivity of the surface charge here. So at a relative high temperature, beyond 150 Celsius degree, at a very small electric field, and then we can see in the bottom figure here, there's a very obvious of the negative shift of the threshold voltage. That's exactly as a NBTI. And then right hand side we see the positive shift here. That's a PBTI. So also at the moment already have certain discovered that the NBTI can be recovered after certain of a moment. And later, when we start to move for the high K metal gate, we start to see that the situation is getting worse here. There's a large BTI in the high K N MOSFET. This is a case with a y-axis as a trapping electron density, and then x-axis is how much amount of the charge you are being injected here. So the bottom one here is silicon dioxide. So we can see the silicon dioxide, even we injected very large amount of charge, but the trapping charge still below 10 to 11. But however, in those high K material, for the technology advancement, we need to have this high K, because as we already previously said, that the silicon dioxide cannot be further scaled, so we need to have this high K material. But the problem is that this high K material cause a serious PBTI issue. So this also pose a very interesting inspiration that on the one side, we want to push for the performance for our transistor or semiconductor technology. But on the other hand, it's always remember that there's always a trade-off between the performance and reliability. Sometimes the performance is way too good, and then the reliability is going to be the very, very worst. This is one of the examples that in the early time, we found that hafnium oxide is very attractive for the semiconductor scaling, that we can avoid the certain leakage current, and we can continue to scale our semiconductor technology. But unfortunately, hafnium oxide is suffering the huge PBTI issues. So this is also another literature. This is getting more and more close. It's not that far away. This is just 10 years ago. This is a paper published in the IEEE TD at the 2014, which just almost like 10 years ago. So 10 years ago, still our high K technology is still suffering lots of the PBTI issues. So this is one of the real measurement result as we increase the gate bias here. Our delta VTH increase here. And also you can see that this kind of trapping is happens so fast. This is a measurements capability down to 10 to minus 7 seconds, which is around like the 0.1 microsecond. So at the case with the 0.1 microsecond, we already see the trapping effect. If we try to develop certain modeling, then you will see. If you want to avoid, to minimize the trapping effect, then you probably need to make sure that your operation can be down to 10 to minus 12, which is not possible because this is in the picosecond range. But in anyhow, it shows that the trapping can be happen so fast. Of course, with the later continuous improvement, finally we find a way try to suppress the PBTI here. This is a paper later published in the IRPS in the 2015, and also it's very important to know that this is industry technology. This is coming from the real 14 nanometer, real 22 nanometer technology. And now we can see our PBTI is below 10 millivolt of the delta VTH. So when we, in the several slides ahead, we show that we set the criteria of the 30 millivolt as a lifetime. You probably will feel like how can be possible so small, because as if you're working in the university lab, if you try to do the BTI in your device, you will immediately get the more than 30 millivolt with less than 1 second. For sure, for all of university produced chip, all suffering this huge issue. So immediately to get more than 50 millivolt, even 100 millivolt with only 1 second stretch. But in reality, what we want is below the 30 millivolt. That's a typical spec, but in the industry product, we can make it as a less than 10 millivolt as a 22 or 14 nanometer technology. But still, we see there's a huge issue for the NBTI. NBTI still remains a concern. And then these concerns not only happen in the 22 nanometer, 40 nanometer, nowadays in the advanced technology, we still suffering the NBTI. So if you try to look at the BTI, you put a Google Scholar put the time from last 3 years, you will see lots of paper talking about NBTI in the advanced technology. That's still the issue that we need to try to overcome. So we try our best to reduce the electron trapping in the hafnium oxide under PBTI, but NBTI will still getting certain issues at this moment. And one of the very important characteristic for the BTI or threshold voltage is not only the shift during the stress, it's also we have to take into account the recovery effect. So the recovery effect means that the real product is always in the on off. The off sometimes means that you just didn't give any bias. If you didn't give any bias, and you will see the threshold voltage shows a recovery when gate bias is reversed or no stress here. So here is one example coming from the NBTI here. So now this is stress at the VG minus below 0 volts. So that's in the case with NBTI. So we can see very obvious threshold voltage shift. But now if we just start to give the bias at the VG 0 volt, then we will see a slightly recovery. But of course, if we give a more negative gate bias, for example here, probably in here, because this is NBTI, and then when we talk about the NBTI, the reverse gate voltage here is a VG, probably like a positive. So then we could see the obvious recovery here. And then also, this is another example, stress, no stress, stress, no stress. So that's in the end, not only cause a threshold voltage shift, but also the ID set degradation. And also it's very important to find out that this recovery has a certain dependency of voltage, also dependent on our temperature. So the high temperature, low temperature will cause a completely different recovery scenario. And this is one of the recovery characteristic. And then you can see that recovery, it causes a problem in the end is that we are not possible to get a fully recovery. It's always a partial recovery. What does mean a partial recovery? It means that in the beginning, this is our starting point. After the certain recovery, we'll never be able to go back to the initial value. There's always the shift between the certain time of recovery versus the beginning of the stress. So that's we call the partial recovery. And the partial recovery causes a huge problem because imagine this is a real product you operate. You stress, you turn on your device, turn off, turn on, turn off. But after 1,000 cycles, 10,000 cycles, then amount of the threshold voltage is still larger than initial one. So in the end, it causes a problem that you got a permanent threshold voltage shift, and then also that will cause the internal problem because of in the end our threshold voltage is not the same like the flash we have, and also that will become very difficult for the modeling and prediction. And one of the unique properties for the recovery, as I say, is that the endless recovery. The endless recovery, that means that we will never able to have the fully recovery. It always has a very slow, but until we don't know when, but it will never going back to the original value here. But also another issue is ultra fast. The ultra fast means that once we have recovery, we stop our bias. We already see the immediate recovery can be happen, and this is a very fast, even cannot characterize. It's a faster than the microsecond here. So that means that if you stop your operation and turn on with a microsecond, you already see the recovery. Turn on with 0.1 microsecond, you see the recovery. Turn on with a nanosecond, you already see the recovery. So in the end, that causes the problem is that we always difficulty to do the prediction. You know, as being the engineer, no matter in which kind of field, what we in the end want to have is a very accurate model that we can do the modeling, we can do the prediction. That will be good for the system designer, that will be good for the user, but in the end it's difficult to make it once we have this BTI characteristic. So there's several possibilities to understand the origin of the different BTI, and one of the very promised right now, because with the time passed by, the understanding has been evolved from the first order understanding, which is in the beginning we believe it's only pure influence of interface state, which here is our interface state. So in the beginning we believe it might be only the reason of the interface state that will cause the BTI. But later we found out that because we try to scale down our dielectric, so our equilibrium electric field is getting higher. If we have a high electric field, we can foresee the electron can be injected inside the dielectric, can be in this region if we have the dielectric defect, and therefore electrons are able to inject into this region. Or further, because in the nowadays technology, we are not only use one dielectric, we normally use what we call this bilayer. We have the silicon dioxide as an interfacial layer, and we have later has a high K as a second top layer. So this also might have the defect in the hafnium dioxide as well. So in anyhow, this dielectric defect will cause the BTI as well. So that's why with a 60 years passed by, finally we cannot still fully understand, because of in the beginning we have very thick dielectric, we only have the silicon dioxide. You know, silicon dioxide is so perfect, so defect inside is very limited. But at the moment we have a 100 nanometer dielectric, we have a 50 nanometer dielectric. So anyhow, we can foresee the only possible can be only trapping in interface. But nowadays, we are not only use a silicon dioxide, we use a lot of high K, very lots of exotic material. And also our dielectric right now is only 10 nanometer, 5 nanometer. So it's possible that this electron can be trapping inside the dielectric as well. So that's our understanding. This understanding is already very popular since 2018. So this is a literature from in 2018. But understanding the NBTI actually becomes another issue. As I say, that nowadays the NBTI still remain as one of the concern here. So in the early time, many different groups try to consider the different physical mechanism to understand the NBTI. And one of the popular model here is a reaction and diffusion model. So the main idea is that we have this interface. We have this silicon hydrogen dangling bond. And once the bond is broken, the hydrogen can be diffusion. So the hydrogen can be diffusion here. And then the hydrogen diffusion will cause the NBTI. So that's the early time model that's coming from the 2003. This is a paper from 2003 IDN coming from the Professor Alam, which is a professor from the Purdue University. So the basic idea is that the interface state density is created by the diffusion limited process, and we have this hydrogen silicon dangling bond here, and then this hydrogen can be diffusion, and then this will cause this NBTI. That's why we see the NBTI, the VTH will shift with respect to the time. And this is one of the examples. They try to use this reaction diffusion model to model this NBTI effect with the recovery, and the result shows very good fitting. That's why in the early time, people believe that the reaction diffusion model can be one of the main cause for the NBTI. But later we found out that that's not enough, because we see that there's a certain issues that the reaction diffusion model cannot fully explain, and therefore later another group proposed what we call the defect central model. But this model is very consistent what we understand for the PBTI. So in the end, that can be as a unified model to both explain the PBTI and NBTI, because in the end it's all related to the trapping inside the dielectric. So once we apply the negative gate bias here, we have the holes here. This is an MOSFET. So we have a holes here. So the hole can be injected toward the right. So we will see the hole injected toward the right here. And then if there's a defect inside the dielectric, then this can still cause a lot of the hole trapping here. And therefore, that's why we can use this model to explain the NBTI as well. So this model suggests that this NBTI is mainly determined by the material and thickness, and also the processing can impact the defect density as well. Because it's in the end, it's all related to the how good or bad dielectric it is. Because in the end, the dielectric can, if once the dielectric has a certain defect, it can cause a PBTI, it can cause a NBTI as well. So later, this model has become quite popular because in the end, we can simply use this model to fully explain the PBTI, NBTI as well. And then also, to understand, to further try to find a way to modeling this defect, people try to consider the different defect distribution inside this dielectric. This is a defect distribution. And then therefore, the group tried to publish all kinds of defect distribution with respect to the different dielectric process. Has a dielectric with aniline, hafnium oxide, silicon dioxide, silicon oxide nitride. So we have all kinds of defect band with respect to the different process that can become the database for the people try to do the modeling to the understanding. And previously, we only mentioned the DC PBTI, which is under the constant bias, but in reality, we have to take into account as a dynamic effect. So the dynamic means that sometimes the NMOS is turned on, sometimes the PMOS is turned on. So therefore, the BTI for the NMOS and PMOS actually is not statically all the happen all the time. It's actually dynamically happen here. So this actually will create these dynamic operations. Dynamic operation of the N and P modes that will cause, in the end, the dynamic BTI. So here is one example, the difference between the conventional static NBTI versus a dynamic NBTI. So now you can see this is a conventional, this is a dynamic, this is conventional, this is dynamic. So under dynamic stress condition, the NBTI are smaller than the static, which is mainly due to the recovery effect. That's why the previous slide we talk about recovery, because the dynamic, it means that sometimes you turn on, turn off, turn on, turn off, but during off, there's a certain recovery can be happen. So we are very open to see during the dynamic stress, the threshold voltage shift is smaller than the static stress here, and therefore you can also start to make it as a lifetime in the case of a static and then the dynamic here. So we can start to see the dynamic result shows up better as a 1.2 volt for the 10 years, which is better than the static result here. And this also in the criteria of the 30 millivolt. So now you see in the advanced silicon transistor, 30 millivolt is very common failure criteria. And also we can try to use several different acceleration model to do the fitting here. So this slide just want to show that we have this experimental result. We stress at this one, this is our lifetime. We stress here, this is our lifetime. But in the end, we can try to extrapolate to the value we are interested in for the 10 years. So in the case with the 10 years, the recommended operation voltage is only 1.3 volt. So that means if you want to recommend that your customer what is the best condition that allow your product for operating for 10 years, and the only value you can tell your customer is only 1.3 volt. And here it just shows that the lots of failure criteria is considered that there is a threshold voltage shift or ID set drift more than 10%. Okay, so here is a summary for this chapter. So in the beginning, we talk about the oxide interface charge. So there's several oxide charge can be possibly founded in the dielectric. And then we also talk about the certain charge transport mechanism, F1 tunneling, direct tunneling, hard carrier, and also the lead current can be increased very fast when dielectric is below 3 nanometer. And we introduce certain CV, GV, DOT as a charge pumping to quantify this DIT. And then also DIT can degrade SS, mobility, noise, And later, if we talk about the BTI, actually we talk about the case of the NBTI, PBTI. NBTI is mainly in the early times talk about this hydrogen diffusion. PBTI is electron trapping, but both can be only described by the defect. Only the defect dielectric, the defect in the dielectric model can both used to understand the PBTI and NBTI, and we see this BTI will impact on the threshold voltage shift, and then we see there's a stress recovery and optimization of gate oxide process it's good to reduce the trap density, and also understand the BTI phases is very important for the lifetime prediction and also reliable CMOS design. Okay, so that's the end of this one. So then we will take a break for 10 minutes at 11, then we will come back for the next reliability issues.
我们是在做卷眉链相关的，然后最近有发现一个有趣的现象，就是我们原本的那个制作电容的基板就是跟外面买，它是 Gate 链的可能都跟 GA 这样子算是平台，然后我们最近在 TSR 有尝试去制作，假设我们把卷眉链 AP 到那个 Silicon Substrate 上发生的事情，原本另外一位伙伴他觉得说，这杯赛要这个导电性，所以他去 AP 在这个 N-type 的 Silicon 上，那我们期待它会变成 可以变成这样子，因为这个成本比较低。
是。
结果发现它变成了一个类似一个 N type 的杀权。我觉得这事情就是蛮有趣，想要请教一下，就是说，我后来想想，是不是因为譬如说他会想这样，譬如说右边才是类似 accumulation 区，左边比较像是 inversion 区，然后因为我的基本这边很多的电子，所以我到这边的时候，它这边会反转出来。
你说原本是 silicon， 后来epi 完都变 N type。
对啊，它这个 silicon 是 N type， 所以买来就是 N type。
然后那这样子，氧化锰变 N type， 比如说氧化锰上面变 N type。
就是整体而言，它好像是不是它就整体很像 N type。
对啊。
所以这个其实蛮典型的，是一个 N type。
对。
因为那时候我们在他那个另外一个伙伴他说，他觉得这个 germanium， 他说察觉我跟他说早班本身就是有点天生带 P type 的缺陷，所以他认为这个应该是一个类似右边的状况。
可是问题是 substrate 是 N type， 它整个量应该会量到整个 substrate 的效果，除非你 germanium 的厚度很厚，
大概150奈。
对，可是
这个是几百麦。
对啊，所以最终我觉得 overall， 如果以这个 CV 基本上是看它这个 carrier 材质可能有没有 reaction， 对，可以跟上频率嘛。那除非你这个 germanium 的这个 carrier 很多，但是 silicon 的 carrier 还是比较容易产生。对，所以 germanium 如果你的 carrier 材质浓度不管它是电动电子，它就是一定还是比 silicon 少。那这样它就会已经被 silicon 影响。
所以其实可以说，假设我们未来用 AP 的技术，其实你要决定它是 N 跟 P， 其实就是看它的基板。
我觉得还是基片是 dominant 的，对，因为 silicon 的这个电子浓度，电子一定还是比较好，容易去被induce 嘛，对吧？那 germanium 如果你这个 quality 没那么好的话，它的 carrier concentration
而且可能又太薄。
对啊，而且重点是 carrier concentration 可能就会比较差。对。
蛮有趣。那所以我想问，因为像我之前有在吹一些 DID， 就是之前在那个，然后重点其实大概就是吹这个。对，
就是看
到落板。
对，就是到那个 SS region。他会看 SS region。
那我想问说，假设未来我们左边的这个技术有研发制成成功了，那我是不是要吹法是要从这个地方往左边吹？就是因为我这个是另外一边。就是以这个 N type 的，因为老师刚刚上课应该是用。可
是我觉得这个很难讲，对，因为我现在不太确定，对，因为最后你要判断你的这个主要的这个inversion mode 在哪里，你要看你的这个电子 inversion 的时候，它到底是在 germanium 还是在 silicon 里面。
所以这样我不知道我这边要怎么去说我的 DID。
对，这样可能会比较复杂一点。
所以老师觉得这种 case 是比较也不是太好说。
对，现在可能有点不太好说。我觉得可能比较好，正常的话可能先做个 TON， 确认一下上面那个 germanium 的它所贡献的这个 carrier 是多少，比较重要。对。
你说这个的结构。对。这我可能回去再想。对。我不太了解。
好。
起来啊，在这边，像这个图，它这个 VTS， 比如它是 MOSFET 的，它就在这边上升嘛，就是在这里是它的 VTS。
就是这个可能要回去看一下它的真实两色图，就主要是用来判断它的 charge pumping current 在哪一点的时候，会因为它 base level voltage 会，这边没有讲清楚它那个实际两侧的那个 base level voltage 这边，因为它是这样子 sweep， 所以你现在不能直接用这个 base level voltage 当做它的 VTH。对，这张图主要是说明它的 DIT 是跟 charge pumping current 是有关系的。
所以这个阶段就是从这边，
这个没有，这个阶段就是这边。
按照这边。
对，这时候会有一个recombine 的 current， 然后就变成 charge pumping current。
所以从这边才去估算它的 I substrate 吧。
对，就是 charge pumping current。对，好，
谢谢老师。
Okay, so we will continue for the next reliability, which will be the time-dependent dielectric breakdown. So in short, we just call as TDDB. So in this chapter, we will only talk about in the case of the silicon dioxide. And also only in the case with a silicon MOSFET. But in general, every technology, every dielectric, always suffering for the TDDB issue. But the learning experience from the silicon base and also silicon dioxide, which is very useful for us to extend to another semiconductor technologies. So first one, so what you will be able to learn here. So first one for sure to understand the physical mechanism, which is always our goal here, especially to understand the difference between the intrinsic and extrinsic breakdown. Also, there's several different ways to testing for the TDB. For example, the ramp voltage, the CVS or CCS here. And also the most important is to understand how to use the Weibull statistic to evaluate the TDB result here, where we have been already talk about the fundamentals related to the Weibull statistic, but now we will use the Weibull statistic in the case of the TDB. And also the different reliability model, population, E model, 1/E model here. So that's very important, and also understand the scaling issues. Why we have a scaling issue? One of the main reasons is coming from the TDDB reliability. So here is outline. Outline is here we first talk about phenomenon, testing, and also very important is breakdown statistic, oxide degradation, breakdown model, and also exertion model, because we need to have this exertion model for the lifetime prediction. And also the last one is some of the several practical cases. So the first one, the phenomenon here. So we have to first to understand that the oxide breakdown is a time-dependent phenomenon. So normally, if we try to characterize our oxide quality, we will have this typical IGVG characterization. We try to characterize our device with IG versus VG here. And then if we can fabricate a good device that has a good dielectric, normally we get a very flat of our gate current here. But this is only in the case with a voltage dependency. There's no actually consideration of the time dependency. But if you try to look at the time dependency, this is a gate current versus time here. And then we always will see this kind of a characteristic. This is a case under the positive gate bias here. So then in the beginning, we very often to see slightly increase and decrease. There's some reason for this decrease. The decreasing of this current is not just due to the measurement error or due to the device issue. It's actually coming from the reliability physics. This part is mainly due to we have certain negative charge. During the stress, we might start to inject lots of electrons inside the dielectric, and we have this current decrease, which is mainly due to the negative charge injection. And later, with the time is longer enough, finally we will see the sudden increase of the gate current, where we define this as a hard breakdown. And once we have this sudden high gate current, that means our dielectric is completely broken. There's no longer insulating property anymore. So the dielectric breakdown means the sudden loss of the insulating property of the dielectric layer after the certain stress here. So that's a typical case when we talk about dielectric breakdown. So in the typical IGVG characterization, we see very flat, and then we saw this might be good dielectric, but with the time as longer enough, we always see this kind of a time-dependent dielectric breakdown. That's why we call this as a TDDB here. So here is some of the phenomena is very often seen in the real semiconductor device here. So we do this as a emission microscopy. So in the case with emission microscopy, once there is a time-dependent breakdown, once it has a breakdown characteristic, we see the bright spot here. We see this one, we see at the edge, we see here. This all indicate that there's a sudden high current goes through, and then high current goes through this part means that this is a region where we have the dielectric hard breakdown here. So how do we do the test? So normally we will conduct as what we call the ramp voltage test here. So we'll apply the very fast ramp. For example, like a 100 volt per second to measure the current here. And then the breakdown voltage is defined as a gate voltage which a certain current increase occurs. And we fix our trigger current as a criteria, and also have to be aware of that the breakdown must be destructive here. So we can try to use this way very fast voltage ramp to characterize our dielectric breakdown. And the reason why we use this voltage ramp, because there's a time factor here. This is suggest for the time dependency. And then also if you try to think about the IG, in here we still talk about the IGVG, but with two different ramp rate, then you will see the huge difference in terms of the gate breakdown characteristic. If you try to measure as a very fast, you get the breakdown. This is a 100 voltage per second. But if you try to measure at a slow of the, for example, 10 volt per second, then you will see the two different breakdown voltage here, which this one is a lower, this one is a higher, and this is because of the time dependent effect. If you try to sweep in faster, that means that each voltage you stress, each voltage you bias is very short. But if you swim very slow, that means each voltage you bias is longer, and that will be easily to trigger the breakdown characteristic. So that has to be something that you also have to be aware that when we do the IGVG testing, the sweeping rate also has a hugely important impact on the results. So here is another example, just try to illustrate the comparison with two different ramp rate. In the case of 2.5 volt per second, this is a case with fast, and this is a case with slow here. So always if we get the fast, then we get a higher breakdown voltage, and then we get a slow, we get a lower breakdown voltage. So if you do the ramp rate testing with the amount of the device, you are not only testing one, you test 100, 200. In this case, is testing on the 340 capacitance here, and you will do this statistic histogram. In the case of a statistic histogram, you will find out there's three different groups where there's a one type breakdown in the very low field. There's a type B breakdown in the medium field, and there's a type C breakdown in the high field. So basically we can divide this type, consider as a different reason for the breakdown. In the type A, which is mainly due to the defect or another defect, which probably due to the contaminate, metals, roughness, this is actually all coming from the process issue. For example, the defect, and so on and so on. So we will consider this part as a one general category, which, because this is coming from defect, coming from process, which is not many due to the intrinsic dielectric property. It's due to the extrinsic factor. The extrinsic factor including the defect, process, clean, uniformity, surface roughness, and so on, so on. So that's why normally we call this as an extrinsic reliability. But on the other hand, if you look at there's a type C, where the very concentrated, very narrow distribution in the high electric field. And this is a case we consider as a breakdown inside, mainly due to the dielectric properties, mainly due to the dielectric physical mechanism inside the dielectric. That's we call as a intrinsic reliability. So it's a very important concept here to understand the difference between the extrinsic and then the intrinsic, because anyhow in the future, once you test the product, you will face the influence coming from the intrinsic and extrinsic, and then to further really evaluate the dielectric property, the strength of one product, we normally will try to evaluate the intrinsic reliability, because this intrinsic reliability is something, the product that we want to sell to our customer. And then the extrinsic reliability sometimes can be eliminated by using a certain screening. So if you do some certain screening, actually we'll remove the device that's suffering from type A and type B, and then we will only sell the device type C to our customer, because the device type A, type E is generally the device that has a yield issue, that we won't sell any product has a yield issue. We only sell the good product to our customer. So we can eliminate the type A, type B by the properly screening. And also, there's two different common testing methodology we call as a constant voltage stress or constant current stress, which the constant voltage stress is the most common one nowadays we use. But to understand the mechanism, sometimes we also prefer to use a constant current stress. So the constant voltage stress means that we stress the device with a gate bias here. So now we will see, normally we see the slightly increase, decrease due to the negative charge accumulation and suddenly hard breakdown. So that's the typical case. But in the early time, if we want to evaluate the dielectric property, sometimes we also consider the constant current stress, because constant current stress means that we try to give the constant current, and then we normally see with a certain moment there's a drop of the voltage here. And then the drop of voltage here is because of, as you know, V is equal to I times R. If the dielectric is broken, is losing its insulating property, the resistance decrease. And once the resistance decrease, means your voltage decrease. So that's a very common to see. The constant current stress will show as a voltage suddenly break down, and then the voltage will decrease. So here's some more details between the constant. This is some more detail for the constant voltage stress. So when we do the constant voltage stress, actually the average field is a constant. So there's a two step here. The first one is that there's a positive charge, and then therefore in here we call as a anode and then cathode is because of that in the early time we only consider the case where we have the dielectric in between. We have the SiO2 in between, and then we have the top. We just put the top as a one metal and bottom as another metal, and the top is how we call the anode, and the bottom is what we call the cathode. So in the first day, we see that the slight increase because in the beginning there's a positive charges, and then therefore the cathode field increase, and then the current increase. But in the second phase, we start to see this negative charge is being injected inside dielectric, and therefore we see the current decrease here. And same, you can try to understand, you can try to really understand the constant current stress is the same that the understanding like a previous slide. And one of the very important characteristics to understand the dielectric breakdown or TDB is what we call the charge to breakdown, because the charge to breakdown is a very important factor. In here, just an illustration of the one of the previous CVS characteristic where we stress and sudden moment we see the breakdown, and then we found out that this degradation scale with a charge here, because that means that if you have a lower current, you need to reach to the certain criteria that can cause a breakdown. So that's what we call the charge to breakdown. But you have a higher current, you have the faster to have the charge accumulation, and therefore you have a lower time to break down here. For example, you inject as a large bias, and you will see the early breakdown here, and that's another TBD. So this is a TBD, where the TBD is a time to break down. And therefore the time, if you try to do the integration of this area, that's our charge to break down. QBD. That's our charge to break down. That's a QBD. And then amount of the charge is always the same as with a one dielectric. The amount of charge can storage in the dielectric is always the same. So if you give a low bias and you have a longer time to reach the charge breakdown, if you have the high bias, you will have a shorter time to reach your charge breakdown. So in the end, the QBD is one of the very important breakdown figure of merit, so to evaluate the dielectric. So we can simply calculate QBD and to understand the dielectric robustness against the TDB reliability. And when we talk about charge per breakdown, that's also very important to see that when we have the oxide scaling. So in these experiments, what they actually trying to do is to consider that you have the source and drain and substrate here, and also the dielectric. So we have the source, drain, substrate, and then what they try to do is to do the charge to breakdown evaluation from the gate side, from the substrate side, which we stress at the gate side is how we call as a gate injection. But if we stress from the substrate side, that's what we call the substrate injection. And how do we do the substrate injection? We just give the minus V substrate. So we can use this way to evaluate the dielectric property, especially the dielectric reliability. But once we see the oxide thickness scale down from this is a 9.5 nanometer down to 7.5, and below there's a discrepancy between the substrate injection and gate injection. That means the QBD seems not a good figure of merit anymore, because once we go to a very thin dielectric, it seems that the charge breakdown is not the main degradation mechanism leading to the TDP effect. There must be something else that will be influence the result. So here is some of the testing structure when we do the TDP testing here. So we have for example, the first one is the area intensive. That we try to evaluate the area breakdown, and then this is our main area we are interested in. So we just make it as a main gate area as large as possible. And also we might interested in the second one is isolation edge intensive, because in lots of cases isolation edges are the weakest area, and also the gate edges here. So we just make a structure that has a lot of gate edges. And also the last one is the gate to isolation intensive. So this just want to illustrate that to test a different weak region for the dielectric reliability, people will try to develop the different test structures. Then the next we'll start to move from the breakdown statistic, and this will be the start to use a certain knowledge where we have been described before. So as we said that the reliability, it's in the end, it's a consideration of the probability. I think so far everyone in this classroom should be able to fully understand that reliability is one thing certainly highly related to the probability that an item will perform a required function under certain condition for a certain period of the time. That's how we call as a reliability. And if we consider a very thin oxide has a good, excellent reliability, that means first of all it has to be the good insulator. That's for sure. That is the first important. It has to be the good, very good insulator, and then also stress the same thing with a comparable voltage, current, temperature, especially in the normal operation condition. So we need to test the the dielectric reliability in all normal operation condition, and also we need to prove that this dielectric has a very good lifetime. So in the previous slide, we have already mentioned that when we try to measure the one device reliability with a huge amount of data, we will first to make it as a histogram, and as this showing, this is a histogram of the huge amount of the MOS capacitance being stressed until the hard breakdown. And we can see there's two different kind of the breakdown characteristic. One is very widely spreading. Why we call this is wide spreading? Because of this is a time scale from 10 to minus 1 to 10 to 5, 10 to 4. So that's a very wide scaling, and also the percentage is lower. So we can consider this is an extrinsic breakdown. But there's one very narrow in the certain of the breakdown time that we consider as intrinsic breakdowns. So the time to breakdown, TBD, is a statistically distributing parameter. Statistically distributing parameter, which can be represented in the histogram or the cumulative distribution function, CDF. Now you probably start to understand why in the beginning, in the several weeks ago, we spent quite a lot of time to talk about CDF, because in most of the case, when we read the semiconductor literature or real document coming from reliability data, nobody will explain why have to use the CDF. They just show the CDF plot like the right hand side here. But if you are the first one to this field, for sure you will get confused. Why it has to be the CDF? But luckily we have already spent lots of time to go through the importance of the CDF. So I believe nowadays you probably can already much easier to catch up the reasoning we use this CDF plot. And also we try to put all this data in this CDF. We found out that the Weibull distribution can fit it, the TDDB data very well rather than the log normal. And the reason why we consider the Weibull and log normal is something we have also explained before. So the Weibull statistic consider as a most common function to describe the distribution data in the case of the TDDB. And the reason behind something we also have been mentioned is because of the weakest link. So now if you look at some more result here, this is comparison between the log normal and Weibull. So we can see that in the case with the log normal, there's overfitting, overestimate here. And then if we look at the Weibull, can be very well fitted, and there's a certain key parameter here. For example, we have the shape factor, which is a beta, which is here. So the Weibull is getting fit better with the TDDB, and normally we can also fit with this is only the TBD, time to breakdown, but also in the early time we can also fit with the QBD. In this graph is a QBD, but it can be both QBD and PBD as well. Both can fit it with a Weibull distribution. That's because of due to the weak limb process. And this one, for low percentage from log normal, is overestimated. So that's why we won't use the log normal in the case of the TDDB reliability. So that's a real case. In the previous part, we only showed that the certain part of the Weibull statistic. But if you try to incorporate every data you have a certain part with extrinsic breakdown. You have a certain part with intrinsic breakdown. Then you will see the whole Weibull plot can be looked like in this case, which we have the part showing here. And the reason why this is here, and also we have this part as here, and this all because due to the different breakdown mechanism here. So like say, this one is mainly due to the extrinsic, this one is mainly due to the intrinsic, but also from the Weibull fitting from the Weibull parameter, we can also observe that this one is very steep. The steep means that we have very large beta. And this one is a very flat, and therefore we have a small beta. But now you can also try to convert this back to the original understanding of our distribution data. Because this Weibull plot is actually original with first plot as a distributed data, and later we make it as a Weibull plot. But now if you try to plot this back to the conventional distribution, then you will realize the large beta here, this one, if you try to plot as a percentage versus a certain value time, for example, in here the value time can be considered between 10 to 4 to 10 to 5, then you will see your distribution, which is very narrow and line in between 10 to 5 and 10 to 5, 10 to 4 and 10 to 5 seconds. So therefore, now you can extend your knowledge with a large beta. It's just actually equal to very narrow distribution. This concept is very important because in the later, nobody will just draw this figure again. No one will draw this figure. If you look at the literature, when everyone talk about the reliability, when they talk about beta, they always say the large beta means better because we have a narrow distribution, and small beta is worse because a wide distribution. You probably will feel confused why. And this is a why, because in the end, no one will draw this anymore. We just look at this beta and come to this conclusion. And also, similarly, if you try to look at the small beta has a very wide distribution from 10 to minus 1 to 10 to minus 4. So if you try to plot the distribution, so then you will see the result here, percentage, and then from the 10 to minus 1 to 10 to minus, 10 to 4, positive 4 here. So then you will see your distribution data set is very wide. So the small beta means the wide distribution. So that's a pretty important implication. Many people, they know how to make it Weibull plot, but few people know how to use the Weibull plot to further understand the degradation mechanism. Also, in this case, suggests us that once you have the different slope, one slope here, if another slope, that means you have a different breakdown mechanism. It's the same as what we're doing for activation energy. Once you have a slope, that always suggests that you have a different breakdown mechanism. So this graph just shows the two different breakdown modes. Normally, the extrinsic breakdown is a critical reliability problem because you will see that lots of the device actually will break down in this range. Some device break down in the 0.1 second, 1 second, 10 second, and this is only the intrinsic can survive for beyond 10 to 4 seconds here. And then the extrinsic breakdown can only be measured if the gate area is sufficient large. This is because of if you look at the small area here, we all know the extrinsic reliability is many causes coming from defect. If you have a small area, you probably have only one defect. So that's a small area. But if you want to see this extrinsic reliability, it's better you try to testing in the large area, and then because a large area you start to have the lots of defects, and then once the defect numbers increase, then you will more easily to see the extrinsic breakdown. So here is some more possible reason for the extrinsic reliability. So I will not go the detail because that's also case by case, but depends on what's your process, what's your dielectric, what's your substrate. So anyhow, the extrinsic reliability is always related to the process-induced defects. So when we try to study the extrinsic breakdown, there's a certain issues. For example, it's a strongly process-dependent difference in the behavior, has a localized weakness, and we need to have the large area capacitance to see this result. And also very important is a very wide statistical spread here. So that's normally the issue of the extrinsic reliability. And normally physical understanding extrinsic reliability is catching more problem because it highly depends on the certain process defects and uniformity of materials. So normally for understand the reliability, we will focus on intrinsic because the intrinsic is something that really due to the dielectric itself and really due to the physical mechanism. But still, some people try to propose several possible models to describe the extrinsic reliability. One of the popular models is this effective oxide thinning model, which if once we consider there's a defect here, then your equilibrium oxide thickness is becomes thinner. So your T effective, which will be equal to Tx minus T defect. And also when we talk about the TDDB, we also have to use the knowledge of this series system reliability. That's where we have been mentioned. If we talk about series system, is a system for any of these components fail. So the reason why we have to consider this system fail is any of one of the components fails, because of when we talk about the areas. Because in the reality, we are not only test a small area of a TBD, we test a big area of our TBD here. So therefore, if you try to look at the MOSFET here, we have the source, drain, we have the dielectric, but this only for the two-dimensional schematic. But if you look at the three-dimensional, we have the big area, big gate area like this one. And therefore, we can consider this big dielectric area as a consideration of the total area A1 correlated with a small area A2. So, therefore, we are interested in the value compared between the A1 and A2. So, for A1 to A2, we can consider this series rule where we have been described before, and with the consideration, in the end, we can lead to this formula where this is a Weibull plot for the A1 versus a Weibull plot for the A2, and there's a one factor in between, which is this one. So that means this is what we call area scaling. So this means that if we actually try to scale the large area 1 to the smaller area 2, actually our distribution will shift vertically with the natural log A1 over A2. Let's just try to look at some of the experimental data. You will get more understanding of this area dependency. So as shown here, this is a right-hand side is a area, the TDDB Weibull plot with area from this value to this value here. And then with a small area here, we have the TBD around 100 seconds. But with a big area here, then we have the TBD between 0.01 to 1 second. So that's a normal. If we scale up to the big area, we always start to suffering for the extrinsic reliability here. But what we can do here is we can also consider to shift the different area and to become the one line together. For example, if we have A1, one big area is A millimeter square. You have A2 here, 0.02 millimeter square. So you can try to shift this one. So that will be natural log A over 0.02, which will be natural log 400 here. So therefore, you can, this is a small area, and this one is coming from the big area shifting here. So therefore, vertical shift between the natural log A1 and A2 which means this is changing from the A1 and A2 here, which is here. Also, this is the same. We can simply to shift every area to the one reference area by consider the natural log of the big area over the small area. That's we call the area dependency. But why we have to do so? You might be wondering why have to make ourselves so complicated. Because in the end, we want to build up the complete Weibull plot from the small time domain to the larger time domain, which is this one. So if we have this data, this is a big area, and now we try to do the area scaling. This shift to this one, this shift to this area, this shift to this area. We all consider the small area as something that we want to as a normalize. Then in the end, we can make as a Weibull plot from very wide time domain. This is a small area. This is a second small area shift to the small one. And then also this is a large area shift to the small one. So normalizing of the breakdown distribution to a reference area is possible. And then now we have this Weibull plot from 0.01 second to the 1,000 second. And this allows us to extract the Weibull slope with a high accuracy, because now we have a very wide time domain for the full curve here. And also for this is normalized to the 10 to 6 centimeter square. And from this one also tell us that we have a one slope here. We have a one slope. We have another slope here. So this is a beta 1. This is a beta 2. And also we found out the beta 1 larger than beta 2. And as we previously already mentioned, the different beta suggests that we have a different breakdown mechanism. So now still back to the same understanding. If one try to do the TDB in the large area and then once increase beyond a certain area, we will see the different breakdown mechanism compared to the smaller one. So that's a very important message for everyone, because once you do the reliability testing, you have to pay attention to your area size. And or one day if you become the customer, you want to buy the product from the one semiconductor company, if they try to give you certain reliability data, you also have to pay attention to the area, because the different area in the end might cause a completely different result because of due to the different mechanism. So this is one example that by looking at the different beta slope, we can also use this way start to think about what would be the possible physical mechanism behind, because different beta slope definitely suggests that there's something different. Okay, so next one we have to understand the oxide degradation. So now we have the statistic tool, and next phase we want to understand the physical mechanism here. So when we understand the degradation, first we have to understand what does mean the degradation. Degradation is a term very widely used in the reliability, not for the oxide. For every reliability, we always use the degradation as a very key term here. So degradation means the continuous gradual deterioration of the oxide property, which is a consequence of the structural damage generated in the oxide. And the breakdown means that it's a trigger when the damage become too large. So we have the breakdown here. So relation between the accumulated damage and breakdown normally we only found in the intrinsic dielectric, intrinsic breakdown. So when we talk about oxide degradation, there's a 5 important oxide degradation. The first one is interface trap creation. The second one is the oxide charge trapping. And the second one is related to BTI, where we have already mentioned. But the third one, which is really unique here, is called the Hall fluence, and also the neutral electron trap generation, and also stress-induced leakage current, silk. The neutral electron trap generation, this is a term that's coming from the very early paper, but nowadays we still use this term. But just want to be clarified, the neutral trap here means the defect. So the first one we will talk about this is the Hall fluence, which is coming from the what we call the Hall injection model. Although this is a very old model, this model is longer than my age, but still right now we still use this model to explain lots of phenomena. So the idea here is once we apply the positive gate bias in the anode side, then as previously mentioned, the band will bending, so we might start to have a FN tunneling. Because of this barrier is become smaller, it's only triangular barrier, so therefore it's only triangular barrier here, so therefore the electron can start to tunnel through this triangular barrier. That's we call the FN tunneling. But once tunnel to here start to gain the energy, and part of electron will become in here. But because this injected electron reach the anode with a very high energy, and this high energy can generate the hot holes. So therefore, we will have the holes generated here. So the holes creations. And then once we have a hose, we have lots of holes. This is a positive voltage, right? So we have a hose. So holes can also tunnel back from the FN tunneling. And back to the another side. And this is this part is the reason to damage dielectric. So that's how we call it an Hall injection model. So this is anode. This is anode side. The hole will be pushed back, injected. That's what we call the anode hole injection model. So this anode hole injection model still nowadays is one of the very classical and it's well known, but everyone believes that this is true happening in our semiconductor. So now based on this model, we start to do the different stress. This is a trap density versus the different injecting electrons here. So these two are based on the FN tunneling, and these two are based on the hard electron substrate hard electron injection. But it's not that important. Right now we won't explain too much substrate hard electron injection, but here just want to illustrate that all the dielectric are breakdown with the same criteria. So this gave us another inspiration, because of no matter what kind of your injection model, use FN tunneling, use substrate high electron injection, in the end, once reach a certain criteria, the dielectric is always breakdown. And also, at the breakdown, the neutral trap density at a low field reaches a critical level. This is a low field here. It's always reach the critical level of the trap density. And this investigation provides us an understanding. In the end, later propose what we call as a population model to understand the dielectric breakdown, because we realize that even with stress at a low field, we still reach a certain trap density. Dielectric in anyhow will still break down. So that's becomes later as a foundation for this population model. So what is population model? We will talk about population model later, but now you have just let you know that even with the low electric field, we still can induce the dielectric breakdown. So there's several models to describe the electron trap generation. The first one is what we call the anode hole injection model. This is where we have been already discussed. The first one, we have the FN tunneling, and second, reach to this region, we have the energy release. Because the energy is so high, so there's a hole generation. And then we have a comeback for the trap generation. So the whole tunneling back castle create the electron traps. This model was very successfully in the early time of the silicon device, because at the moment we have very thick dielectric. We have a silicon dioxide around 50 nanometer. We have a 100 nanometer. So we all use the anode hole injection. But later, once we do the scaling, we scale down, we thin down our dielectric below 10 nanometer, but we don't talk about the anode hole injection anymore in our advanced CMOS, because below 10 nanometer, we have some other fundamental degradation mechanism. But interesting is to look at that in another technology, for example, the wide band gate technology, in case of the silicon carbide in gallium nitride, we still use a very thick dielectric because we have very high electric field. And in that sense, nowadays we use an anode hole injection model to explain everything in the silicon carbide and then the gallium nitride device as well. So the next one is what we are here, trap generation model, is an electric field energy model. This is mainly due to the electric field induce sufficient energy. and this will directly into the oxide and cause the electron trap creation. That we call as a trap generation. And also the last one is a hydrogen release model, which is related to what we already mentioned in the NBTI. There's a hydrogen, there's a dangling bond, and the hydrogen will be released. And once released, they will also generate the traps as well. So the degradation phenomenon, another one is what we call the stress-induced leakage current. The stress-induced leakage current is mainly due to there's an additional current component add to the FN tunneling, and which is caused by the trap assistant tunneling here. So for example, we have the Venn diagram like here. So as we know, once we give the positive bias, we always have the FN tunneling. This is due to the FN tunneling. But once we have the defect inside the dielectric, we might start to have the trap assistant tunneling. This is a trap assistant tunneling, and this will cause additional current. And that's why we call this as a silk stress-induced leakage current here. And here we can look at some of the example. You can see this is a real device example. This is a device being stressed under the constant current stress. And in the beginning, the flash is here. But after stress, we look at the IGVG again. And you can see that after each stress, the gate current start to increase. This is mainly due to the stress-induced leakage current, and which is, in this case, is mainly due to the high injective fluence here. So that means we inject a lot of charge, induce a lot of defect, and therefore our current is getting higher. And there is always a one-to-one relation between the silk and then the trap density here. So this is a current, and this is our trap density. So, since the neutral trap density reach critical value at the breakdown, the silk also will be used as a degradation monitor and predictor. So here is a summary between the different stress and then the different degradation. So we have the oxide field, which is mainly due to the CVS. We have the constant current stress induce a different current density, and all that can lead into the oxide degradation, which is mainly due to the generation of the neutral electron traps. That's defects. So we have several possible ways related defect: interface trap, trapping charge, hole fluence, oxide trap, silk, and then breakdown when critical trap density is reached. And because of this understanding of the lesser critical trap density reach, come out with the understanding of the population. Models. So because next week we have the presentation, I also need to make sure next week I'm able to finish the TDDB. So I will continue to talk about the oxide breakdown model today, and then next week we might start having more flexible time for everyone. So, but if you are busy, you can leave earlier, but I think our TA will distribute the homework after this class. So probably I think I need another like 20 minutes for try to finish this oxide breakdown model. We will leave for the lifetime acceleration in the next week. So regarding for the oxide breakdown model, here we have seen that there's a certain understanding for the population model. So the population model here, we have seen that related to the thickness dependency, and then the critical trap density, and also the area dependency. This is all in the previous we have been shown that we have seen the dielectric breakdown has a thickness dependency, has a critical trap dependency, has an area dependency. That's why in the end we propose the population model. Later we will talk about population model. Also, there's a very important aspect between the hard breakdown, soft breakdown, and then the progressive breakdown. Because in reality, you will not see the TDDB curve. That's just as we show in the first page. In the reality, it's always show the curve like here. So we have the gate current versus the time here. The first page what we show is a very limited in the case with a very thick dielectric, where we start to see the hard breakdown here. But this only in the case with a very thick dielectric. But if we try to look at some of the thin dielectric, we actually will find out that the curve has a slightly different. In the beginning, it's still the same. We have a little bit decrease, but later we will see slightly increase. And then we start to have a noisy, with a certain noisy for a while. Finally, we see the hard breakdown here. And we still define this part as what we call the hard breakdown. But the point we start to see a little bit noisy. The noisy is not just a measurement artifact or not a measurement errors. It's really something happening inside our semiconductor device. That's called this noisy. And the onset point for this noisy is what we call the soft breakdown. And then in between of a hard breakdown and soft breakdown is what we call the progressive breakdown. And in lots of cases, you will see this phenomenon. It's very often seen. So this is very important because this is a reality case, how you see the time-dependent dielectric breakdown. So what is actually the population model? So first of all, we have to understand that the electron traps are randomly generated in the oxide. So first of all, it's randomly generated. So that's why we come up, we have to use certain probability and the statistic here. And then if you try to think about, this is your dielectric here. And first of all, we might start to generate the defect in this place because our defect is randomly generated. So we don't know where the defect can be generated, but we knew it will generate it. But it can be in the first place. It can be the second, next second, third, fourth. But as the time passes by, you might start to see the defect can be randomly connected with each other. That just needs a time, and then just matter with the probability. We don't know, but it will happen. But with the next, it could be here, and next, it could be here, and the next can be here. And finally, as the time longer enough, has a chance that the defect will be connected with each other and become the one line from the bottom to the top. And this is a moment where our electron can start to go through and become the conducting path to the other side. So this will become as a conducting path. So this is a moment where we start have the breakdown. So the breakdown when conducting path is formed from anode to cathode. So that's how we call as a population model to understand the time-dependent dielectric breakdown. And then the critical trap density can be calculated as a total number of traps over test value necessary to form a conducting path. So that means that no matter what kind of your stress, you use a high field, low field, as long as reach to this critical trap density that will form a conducting path, we will have the TDDB, we will have the time-dependent breakdown here. And this also is perfect to explain why thin dielectric, if you imagine, why this model is very useful, because this model tells us if you have a thin dielectric, you have a thick dielectric. In the case with a thin dielectric, we probably only need 3 defects. That's enough to form the TBD, and that is fast because we only need 3 defects. So the TBD is a small. But for the very thick dielectric, we need a lot of defect. We need 1, 2, 3, 4, so on together. And also it's very crucial that these defects are randomly generated and randomly connected. So to have so many defects being connected with each other, it takes a time. So PVD is large. So that's why this population model is very important, because of course, if we don't have a population model, it's still very intuitive to understand that thin dielectric, you get the breakdown earlier, the thicker dielectric, you need a more longer time. But anyhow, with this model, we can perfectly explain the TBD, and also with this model, we can perfectly explain the Weibull distribution and so on and so on. So once we start to adapt this model, we can start to have very statistical modeling. This is a case with considering the oxide with the 9 nanometer and with each defect of this radius around 0.45 nanometer. And this is simulation based on the population mass model is very well fitted with experimental data. And also, with consider this model, we can have very great simulation to understand the dielectric thickness, impact of the dielectric thickness. So in the right hand side, we see that this is an experiment. So we have see the thicker dielectric, we have a large beta. The thinner dielectric, we have a small beta here. But also for simulation, we show the same conclusion. This is 12 nanometer. This is 3 nanometer here. And also, this tells us that when the oxide thickness is decreasing, Tx is decreasing, the beta is small. And when Tx is increasing, the beta is large. This is because of the population model and the defect distribution. You can think about this. If you don't understand, you can ask me, because of anyhow you will find out that this is you have a thinner dielectric. You get only 3 or 5 to trigger for the breakdown. So your beta is pretty small. You have very wide spreading because it's easily to have a 3 to 5 defect connected to each other. But if you have very thick dielectric, you need so many defects, and therefore your beta become large. Your distribution is very narrow here. So the statistical of population model explain decreasing Weber's law for decreasing oxide thickness. The decreasing Weber's law is because of the large spread of a TBD, because of once we decreasing the oxide thickness. And also, this is another result where we have the Weber's law versus the oxide thickness. So the decrease of Weber's law for thin oxide is an intrinsic statistical property for the degradation mechanism. And also, if you look at this, is one of the results for the critical trap density. So now we try to look at the critical trap density when the oxide thickness reduced. And then you can see the left hand side means that when you reach to around 0.9, this is a size of 0.9 nanometer. This is a 2.5 nanometer of a defect here. And then you can see that with the oxide thickness decrease, you probably only need one defect. That's enough to trigger for the breakdown, which is a very important warming. Only one trap is needed to form the conducting path. That's why this becomes a huge warning when we do the semiconductor scaling, because we realize that we cannot scale down our dielectric below 2 nanometer. We cannot scale below 1 nanometer because anyhow, only one trap is enough to trigger for the TDDB, and only one trap is enough for the population path. And this is another evaluation of how people try to look at the defect generation rate. This is based on the silk measurement, and this is the defect generation versus gate voltage here. So we can find out that the defect generation is exponentially dependent on the gate bias, and then defect generation is independent of oxide thickness and also the gate area. So here is also another literature reported that the Weber's law is related to the critical trap density here. So that's another literature who published that the Weber's law is related to critical trap density. And therefore, once we thinner down our dielectric, while our beta is also decreasing, one of the reasons is because of the critical trap density is reduced as well. So this is area dependency. Last time, previous slide, we also talked about the area dependency. And then if you try to look at the area dependency of the charge to break down, and this is a case of the Tx equal to 11 nanometer. This is a Tx equal to 4.3 nanometer here. So therefore, the QBD is proportional to the TBD here. So between the area between the 10 to minus 6 and 0.1 centimeter square, the lifetime will drop 3 to 4 orders of magnitude for 4 nanometer, but only factor 2 for the 11 nanometer. So this is actually means that this has a huge drop in the case with a thin dielectric for lifetime. So that also poses another warning that if we continue to decrease our dielectric, we always face a lifetime issue because the lifetime will drop very fast. Okay, so we will stop here and we will continue for the next week. And the reminder that next week we will have the presentation from the first group. And then if you have any question related to a presentation, just feel free to let me know. Also, you have to send me the slide 1 day before and then print the slide to me for the grading. Okay, so see you next week.